Okay, so here's where we were last time. We were talking about the cross product. We didn't quite finish the section on cross product. I just kind of want to wrap that up real quick, and then we'll move on to the next section. So we defined a bunch of stuff, right? We defined this idea of right-hand order, left-hand order. We defined determinant, talked about some geometric features of determinant. And then I introduced the cross product with an algebraic formula. And then from that algebra, we started making various connections and using what we know about determinant to draw conclusions about how that relates to order and area and volume and various different things. What we ended up with, in fact, was a complete geometric characterization of the cross product. It was defined algebraically. Now we can give an equivalent characterization using only geometry. So let's just remind you of these facts that we know about it. The cross product has the following characteristics that are unique to the cross product. It's perpendicular to both of the input vectors. Right? So it's along a line kind of like that. Its magnitude is equal to the area of the corresponding parallelogram. So, you take those vectors, make your little parallelogram like that. That tells you how long it is. And finally, this list, V, W, V cross W, is always right-hand order, asterisk, or possibly one of the vectors is 0, and then it's trivial. But, so other than that, so most of the time, right-hand order, certainly never left-hand order. So I'm going to represent that on here with 1, 2, 3, thus indicating that it's that vector. Yes.
Is that true even if it's the other vector?
But it's not the other vector. That's the point.
Okay.
Yeah, it is. There is between these two vectors, only one of them would make this list a right-hand order. And so the cross product is the one that makes it the right-hand order. Yeah, right. So this is a complete geometric characterization. You could, I suppose, it'd be weird, but you could say, at the very start of this discussion, you could define the cross product as, well, it's the unique vector that has these characteristics. And then you could try to work backwards kind of through the arguments that we've done here and eventually derive a formula for it. It's just weird and hard to do it that way. So that's why I do it this way, where I start with the formula. Nevertheless, the fact that, why do we choose the definition of cross product the way we did? Because it has these cool geometric characteristics. Right? Okay. So these are really the motivation. These are not fringe benefits. These are the motivation in the first place. Okay. So a real quick observation, so one of the first properties that we wrote down about the cross product was that V cross W is not W cross V. Remember, algebra doesn't always work the way it did in high school, right? The algebra of cross products is weird and dangerous in the sense that if you're too loosey-goosey with, this is how I always did things in high school, you're going to make mistakes. This is one of the big ones. It's not commutative. So now, even though, you can prove this with just algebra, you just write it down, right? It's easy to observe that this is the case algebraically. You can take a geometric point of view on this as well. So these two vectors, we know they're the same length because the length of each of these comes from looking at the exact same parallelogram. Same area, therefore same length. Right? They're both clearly perpendicular to both V and W. The only question is, do they point the exact same direction or do they point the exact opposite direction? Right? And there's different ways to see, how they point in opposite directions. One easy way to sort of geometrically, literally hand-wavy way to see it is, if this is V and this is W, then this is V cross W. Right, apologies to those watching on the video. I'm doing a hand gesture. So VW, V cross W. If you want to do W cross V, now all of a sudden W here is the first vector. That's the second vector. So your hand gesture has to be like this. Therefore, W cross V is down and the other way. Right. So that's a sort of an easy, I think, very satisfying way to see that they point in opposite directions. Or if you like, we know that's a right-hand order. We know that's a right-hand order. First vector, second vector, cross product, those are always right-hand orders. Asterisk, unless one of them's 0, which is not something we need to worry about, because it's always obvious. If you switch two vectors in a list, we know that switches the order. Therefore, this second listing is clearly a left-hand order. And then you just look at these two, same first vector, same second vector. These two different vectors that we're interested in give opposite orders, and therefore they don't point in the same direction. So there's a more algebraic way to see it, but anyway, suit yourself. Okay, all right, this last example I'm going to let y'all read. It's a pretty straightforward read. It's just a matter of interpreting a cross product purely geometrically, using the properties we just talked about to conclude the cross product without using the algebra. And I think it's kind of a neat example, but it's just, and both of these. Pretty immediate applications of the ideas we just talked about. Okay, so moving along. Next section, lines and planes. Reminder, this course is called Multivariable Calculus. We haven't done any calculus yet, right? And why? Well, because we're focusing on the multivariable part right now. We're dealing with, what is this three-dimensional world in which we're going to do the calculus eventually. So right now we're exploring R3 and how to describe lines and planes in R3 is a big aspect of that. So we will get to the calculus. Just, give it a little time. Okay, so first of all, I want to talk about what is an equation, just to be perfectly clear, right? An equation is an algebraic statement. It has an equal sign in it, so that, right, this is a pretty easy definition. So what do we mean by the equation of a shape, though? And now y'all are accustomed to, when you say the equation of a line or the equation of a parabola or whatever, that it's an equation that you write down and then it, somehow relates. I mean, look, come on, it's the equation, for that geometric figure. But let's just, again, be blunt about what does that mean. Here's what it means. An equation of a shape is a test. It's a way to test points. If you come to me with a point, and if it satisfies the equation, that means that it is on the shape. And on the other hand, if that point does not satisfy the equation, then it is not on the shape. It's a point tester. Yeah? Everybody on board? Just to have that for the record. Okay. So lines in R2, yawn, Algebra 1, right? Ancient history, high school, middle school? Is it middle school? I think possibly 8th grade, right? So y'all have seen this for a long time. I like to point out, just from my own personal experience, this used to be my favorite equation for a line. And I'll tell you why I like this. Well, because this equation, the whole mx plus k, m, meant something. I could interpret something about the line based on what that number m is. It's the slope, right? The rise over the run. So the form of that equation tells you something geometric about what you're describing, and that's lovely. It's a connection between algebra and geometry. Mathematicians love it when there's a connection between algebra and geometry. That's got it right there. So, cool. This k here means something geometrically. It tells you where this line intersects the y-axis. Geometrically significant, right? Whereas, what's A? Right? Where does that show up on this picture? Right? What is B? Where does that show up on this picture? Not at all clear. C. What does that mean? And it kind of, certainly in my middle school or whenever that was, math classes, no such geometric connection was given. And so I just thought, okay, well, this is a bad form. Right? This is, I suppose it's algebraically organized, right? It's, this many x, this many y. All the variables are on the left, all the not variables on the right. I guess it's got that going for it, right? Nevertheless, I didn't like it. Okay. This is now my favorite equation for a line, and it's because I now understand what these numbers represent. These numbers actually do mean something. And why didn't they tell me this in middle school? Well, the reason they didn't tell us in middle school is because we, at that time, did not have the appropriate tools. And the appropriate tools, depending on how you look at it, the idea of vectors and the idea of the dot product. Okay. So, alrighty. That's just a little context. Let's start from nothing. Suppose we don't know anything about the equation of a line. Recall that the equation of a line should be a test. I'm looking for an equation that if the point is on the line, it does satisfy the equation, and if it's not on the line, and it does not satisfy the equation. And how would I do that? Let's suppose that we're given a point on the line, and that we are further given a vector perpendicular to the line. Now, that may seem like an odd choice. You'll see the motivation in a moment. But let's recognize first, before we go on, that if you tell me a vector in perpendicular to that line, and if you tell me a point x naught on that line, that does uniquely characterize that line. There is exactly one line that's perpendicular to n and that goes through x naught. Yeah? Okay. All right. So now, how do we test this point then? Let's see here. I'll do this in yellow. Given the n, given the x naught, how would I decide if this is or is not on the line? Okay, so here's an argument I can make. It comes down to looking at this difference vector. Let's look at x minus x naught, which you'll see if it's on the line is this, if it's not on the line is this. So this red vector, x minus x naught, and I make the case that if the point is on the line, x minus x naught is parallel to the line. If x is not on the line, then x minus x naught is not parallel to the line, right? So what we have now is a kind of a, it's not clear how useful this is, but we have a crisp geometric test of whether a point is or is not on this line. Okay, so let's go to write this down. It comes down to whether that difference vector is or is not parallel to the line. Okay. All right, now we're going to take this test that we have here, and we're just going to start playing with it, manipulate it around a little bit. Go back to this picture. I appeal to your geometric intuition. If this red vector is parallel to the line, then it is, you'll notice, perpendicular to that n vector. Right? That's an if and only if. Parallel to the line means perpendicular to the n vector. Now, I hope everybody had like a little instinctive, knee-jerk reaction there. Somebody said perpendicular. I hope you'll develop this reaction going forward, that when you hear the word perpendicular, the very first thing that should jump into your mind is, I know how to test that. Perpendicular means dot product is 0. Right? Really nice tool. So, perpendicular to n means that dot product is 0. This is where kind of the magic happens. We have now transitioned from geometric statements that are hard to test. We've now transitioned into an algebraic statement, which is easy to test. Right? If these things are given numerically, then I know how to test. Punch up this arithmetic. See if you get 0, you don't get 0. Snap. And now I'm just going to kind of rewrite things. Distributive property, move one term to the other side of the equation. Right? Nothing happened there, really. And now let's not forget this n vector. See where I was using this color. N has coordinates a and b. X has coordinates x and y. So n dot x, n is AB, x is xy, so there's what the dot product looks like. And by the way, I mean, let's not forget that, n was a given, x naught was a given, so that dot product is just some value that I can just compute. Right? This value on the right, n dot x naught, is always the same value independent of the point that I'm testing. I'm testing that yellow point x. I don't have to wait for someone to tell me what point they're testing for me to be able to punch up that right-hand side. It's just, it's a number, whatever that is. Let's just call it C. Okay. And look at what we got. Right? Here's that equation that I did not appreciate in middle school. This is the equation of the line, and it comes straight out of a clearly geometric test. The upshot is that you can sort of turn this around backwards. When you have an equation in this form, these two numbers, A, B, tell you the in vector that is perpendicular to the line. That's a very strong geometric interpretation, right? Going back up here, what do these things mean? What's the A? What's the B? Oh, individually, it's not clear what they mean, but together, AB tells you a normal vector. Everybody on board? Okay. Why didn't they tell me this in middle school? I was legitimately annoyed when I first learned this. Okay, but you can see why, right? I mean, in order to appreciate this point, you have to understand what a vector is. They don't do that in middle school. And in order to be able to see why it's true, you need to be able to talk about dot products, and certainly they don't do that in middle school. So, it makes sense. I get it, but it's still frustrating. Okay, now, I'll point out that even though they're really morally the same equation, this one, that is what you'll actually be writing down, has a slightly undesirable feature, and that is, even though it's explicit, every single scalar variable is right out, you can see them, this form does kind of conceal what's really going on. So I actually, in my own personal preferences, I like this form better. Even though it's not explicit, ax plus by, just completely spelled out, this form of the equation tells you, it's staring at you right in the face why we like that form. We like that form because the left side is a dot product. That's something that I have interpretations of. Right? So that's an aesthetic point, but when I think of equations of lines in the plane, I think this. Not so much this, although of course they're exactly the same thing. And when it comes down to writing out the equation, you should probably write it like this because it's explicit. But I think this. Okay. All right. So easy example. Suppose there's a line that goes through these 2 points in the plane, and let's see here. So just to have something to look at real quick. 1, 2, 6, -1. So here's that line. How would I find the equation of that? Well, I can take the difference of those 2 points. That gives me that vector. That's clearly parallel to the line. Right? Let's see here. Now, I need a vector perpendicular to that. Neat trick. I hope you all will internalize this one. If you want to find a vector perpendicular to another vector in the plane, just take the 2 coordinates and switch them and stick a minus sign on one of the coordinates. Your choice. Right? And it just always works. You can see how the arithmetic, right? We're going to have 5 times 3, then we're going to have -3 times 5. You add them up. The dot product, in other words, is clearly 0. When you do that trick, switch and add a minus sign. Right, nice trick, yes.
But only to one. Right?
I'm sorry?
Only you add a minus sign only to one.
Yeah, you add a minus sign just to one of the coordinates after switching. That's right. And which one you do sort of decides which of these possibilities you'll get. Yeah, absolutely. Yeah. So having made that observation, give me 2 seconds. Having made that observation, I see 3, 5 is perpendicular to the line. Yeah, go ahead. What's that?
I'm just saying you can assume it's parallel because the line goes through the 2 points.
Yeah, so this is just a geometric observation. If you have 2 points that are in a line, now let's be very careful here. When I say in means location. Location means I'm interpreting them as points. So, but then when you say subtract them, okay, wait a minute, so what does it mean to subtract 2 points? We don't really technically have a formula for subtracting points. You then have to reinterpret those points as position vectors, and then when you subtract the position vectors, that's when you get this vector that's clearly by picture, parallel. Yeah.
Okay. And so you wouldn't be able to assume that if it didn't tell you that the line explicitly went through.
Correct. It is key that the line goes through. Through is a way of saying these points are in the line. Yeah, exactly. Right. Okay, so we've got a vector perpendicular, and recall that once you have a vector that you know is perpendicular to the line, that vector, you can view that as your in. Right? And now all we need, in order to finish writing down this equation, keep in mind our goal is to have a test. I need to know what is the in, and now I'm also going to need to know what is the x naught. And once I know the in and the x naught, I'll have a way to test that x vector. Right? So all that remains is what? Oh man. Okay. Let's see. What is that x naught? I just need x naught to be any point in the line. I have two of them, right? Our cup runneth over. Pick one; it doesn't matter. Whichever one you find most convenient to the arithmetic with. So I guess I like the smaller numbers here. So I'm going to pick that one to be my x naught. That goes there. Oh, come on! It's hard to get that to So there's my x naught, and then just write it all down, and there's your equation of your line. Everybody on board? Okay. Now let's step it up to 3 dimensions. And all the stuff previously was really kind of just a redevelopment of ideas from middle school. College level perspective on old high school, middle school level questions. Here's a new kind of question that they don't talk about in middle school. If you have a plane in space, 3-dimensional space, how would you write down that equation? And it's a ripoff, total ripoff of the previous idea. I'll first argue that if you give me a vector perpendicular to the plane, and if you give me a point, what color did I use? Oh man, I forgot. I think I used light blue. A point that's in the plane that uniquely characterizes that plane, right? There's a bunch of planes perpendicular to that in vector, right? But only one of them goes through a given point. So these two geometric objects uniquely characterize that plane. Observation, if you want to test whether a point is or is not in the plane, whether the difference vector is or is not parallel to the plane. That's the perfect test, right? You'll notice this is just, again, shameless ripoff of the argument that we made in the context of lines. Everything goes through the same. Parallel to the plane means perpendicular to the normal vector. That means dot product is 0. Shuffle the algebra, and you end up with this same dot product equation right there. How we doing? Is everybody on board? Okay. Now, it looks the same. It is a little bit different. I mean, this equation, let's recognize this is no longer a dot product of vectors in R2. This is now a dot product of vectors in R3, right? So it is a little bit different, and you can see that more visibly when you extract that dot product out, multiply out that dot product. Well, there's vectors in R3, so now you have AX plus BY plus CZ, so it's a little bit different, appropriate to the context. But it remains that these numbers, A, B, C, are just the coordinates of that vector that was given to be perpendicular to the plane. So, again, neat fact. When you have the equation of the plane given to you, reminder, an equation is a test. When you have, the algebraic test of whether points are or are not in that plane given in this form, those numbers, A, B, C, are telling you important geometric information about the plane. They're telling you a vector that has a really important characteristic in relationship to the plane, namely it's perpendicular. Pretty good? Okay. while I'm thinking about it, real quick, observation, I suppose. What would happen if I took this equation and multiplied both sides of the equation by some constant, k, let's say. So let's do that. I get k-a-x plus k-b-y plus k-c-z equals k-d. This is, really a just as good equation for that plane. And objection, these numbers, the coefficients of x, y, and z, are not the same as they had been. That's not a, b, and c anymore. That's now ka, kb, and kc. But here's the thing, that then is just a scalar multiple of the other in vector that we were looking at. All this is saying is that if you have this vector ABC perpendicular to the plane, any multiple of it is also perpendicular to that plane, and in the sense of how it serves its role as being a vector perpendicular to the plane, it's just as good, right? So it doesn't matter which normal vector which in vector you pick. Any vector perpendicular to the plane is fine, right? There is no magic right vector perpendicular to the plane. So feel free to scalar multiply however is convenient. Like if you end up with an equation that has fractions in it and you want to multiply through by the common denominator or something like that, that's cool. Totally fine. Okay. And now my grammatical slip up. I've not yet defined this term. A question, why do we use the letter in to represent this perpendicular vector? It is because it is sometimes referred to as a normal vector. The word normal in the context of vectors is intended to suggest perpendicularity. Right? So thus in instead of v or something like that. Okay. So yeah, we'll commonly refer to this as a normal vector. Okay. Related puzzle. Suppose you're given 3 points in the plane, so it goes through each of the following 3 points. Now, as long as those points aren't collinear, clearly there's going to be a unique plane that goes through all of them. Right? So how we would find the equation of that plane? Well, we need to find two things. We need to find a normal vector, and we need to find a point in that plane. Okay, well again, I have 3 points in the plane, so that's not a problem. Take your pick. Suit yourself. Who cares? But how do we find that normal vector? Okay, well, this is the thing we're looking for. Normal vector. That normal vector, I observe, well, it being as it is perpendicular to the plane, it's also perpendicular to these two vectors, p minus r and q minus r. So a rephrase is I'm looking for a vector in that is perpendicular to two known green vectors. How do I find a vector perpendicular to two given input vectors? Oh wait, that's this really convenient property of the cross product. So just flash back to Wednesday's talk. The cross product definitely has this property, and it doesn't really matter how long it is. I just need any vector that is in fact perpendicular to the plane. So how about we just pick the cross product? Make that your normal vector, and now you're up and running. You have your normal vector. Take your pick of which one to be your x naught. Plug in. Everybody good? Okay. What about a line? Wait, we've already talked about lines. Right, but we've talked about lines in R2. We've talked about planes in R3. What if you have a line in R3? Can you do the same thing? And it turns out that it's not, kind of, sort of, but not in a very satisfying way. It's definitely different to try to describe a line in R3 than in the previous two cases. So now here's where I'm going to call back to the very first observation I made about equations. Right? I made this observation of what an equation is. Right? Most fundamentally, an equation is a test. If the test is satisfied, the point is on the shape. If it's not satisfied, then it's not on the shape. Again, that is the connection between the algebra and the geometry. The equation of a shape serves as a test. Okay, we're going to come up with some algebra that describes a line in a totally different way. We're going to write down some algebra that doesn't test points. It relates to the line by generating points on the line. And so it's not a test at all. It's a generator, right? So parameterization is what we call this. A parameterization of a shape is algebra that generates points that are on that shape. Totally different function. I don't mean that as a mathematical. Totally different. Purpose of the algebra compared to an equation of the shape. All right. So here's how you do that with lines. It's not that big of a deal. If you give me a point on the line, x naught, and if you were, let's say, to give me some vector parallel to the line. Now, keep in mind, this v thing is a vector, right? I'm thinking of it as a vector, not as a point. So I can't say where v is. V is just a direction and a magnitude. So there's v. Right? But I make the observation that this construction, by which you start with a point on the line and then you move parallel to the line by some distance, okay, so therefore, like that, that point plus that parallel vector will give you another point on that line. Right? So this construction, x naught plus tv, if x naught is on the line, if v is parallel to the line, x naught plus tv will always be a point on the line. Cool? Therefore, this is a point generator. So specifically a point generator in that, again, with these two things known, x naught known, v known, you can just start plugging in any old values of t, whatever value of t you want, no constraints. Plug in that as a raw material. Out comes a point on that line. Right? Notice equations don't do this. Equations can you come to me with a point, then I can test it with my equation. But the equation doesn't make points. Naturally, immediately. Likewise, the parameterization, while it does generate and make points, it doesn't test. This isn't. You can't, plug in some x and then ask immediately whether or not this works. I don't know. How would I find the t? It's not clear. That's not what this thing is about. It serves an entirely different connection between algebra and geometry. Yeah. Yeah. I'm sorry. Did I see your hand? I just had mental note. Yeah.
Just for the t, real quick go.
Yeah, it's just a scalar multiple. I'm going to give you a different point of view in a second, but I was just thinking of this as any multiple that you multiply by, v. So there's v, right? If you multiply by, well, let me do it more consistent with what I did before. You take that v and you multiply it by any scalar, you're going to get another vector that's also parallel to the line, but just with a different magnitude. Probably different magnitude. Yeah. Right. Yes?
Why is x0, why does that have like a vector symbol over it? It's just a point.
Right. So, my own personal preference on, how to use notation is to always conflate the notations between points and vectors, because context always makes it clear what I'm actually talking about. Right? So I could instead of calling it x naught vector, I could give it a capital letter name and call it capital A. Right? And then it would look like a point, right? But, the slight problem with that is, then I have to write down separate definitions of what is a vector plus a vector. Then separate, what is a point plus a vector, right? Because if we're writing them as different things, then this is a different operation, and I just don't want to have to deal with that. I just find that clunky, right? So my convention in this course is going to be that with full recognition that yes, points and vectors are different. They are in a perfect correspondence. Context always makes it clear which one I'm talking about, and so I'm not going to make the distinction in my use of notation. And then you just, look at the picture to see which one it is. Right. Very good question. Thank you for that. Okay. So here's a different way. So somebody asked, what's T? What does T represent? And when we first wrote that down, we were just thinking of T as, well, it's any scalar multiple, anything that you're going to multiply by V, and observe that it always gives you a point on the line. So it was just an raw material input that goes into this little factory that spits out points on the line. Okay. So here's a different way to think about it, though. You can think about this T as being time. So let's pretend that T is time, and let's just hit the play button and see how does this little movie go. When T is equal to 0, plug in T equals 0 there, and you get X is X naught plus 0, and so you get that point. Now let's plug in T equals 1. When T is equal to 1, you get X naught plus V. That gives you that point. Now what about when T is equal to 2? You get X naught plus 2V. When T equals 2, you get that point. So as time passes, thinking of T as time passes, you are just moving along the line. Right? So this perspective on how to interpret T gives you this interpretation of how the parameterization generates the line. It generates it by literally tracing it out. So this is a very handy little geometric perspective, metaphor, if you like, whatever. It's a way of thinking about how do parameterizations work, because we experience things in time, right? That's the human experience, right? Things move with time. So it's very satisfying, and you may think of T as time. We are not saying that you have to, right? You don't have to at all. You can think of T as just being a number. That's the raw materials that goes into this point factory, and out of which comes points on the line. But very often, really convenient. Okay. I do want to make the observation that there are different ways to trace a line. Observe. Watch me trace this line here. Right, so that's one way to do it. Here's a different way to trace that line. Right, see the difference? Right, in one of them I was going slower, and I started at one place. The second way that I did it, I was tracing it faster, starting from a different place with T, when T equals 0. So those are different ways to trace the line, and all that points out is that there are different ways to parameterize the same line. So if you look at these two parameterizations, let's look at this one versus this one. They look like completely different parameterizations. Now, none of those things are familiar, right? But notice this starting point on this parameterization is exactly what you get when you plug in T equals 2. So that starting point here is on the line on the left. Right? So these lines intersect. Furthermore, these vectors are parallel. One's clearly a multiple of the other. Right? So what we're talking about, these two different parameterizations that we have here are parallel and intersect. They're the same line. Right? So don't make the mistake of thinking that that you can talk about the parameterization of a line. There's lots of different parameterizations of lines that look totally different, unrecognizably at a glance, right? So you can talk about a parameterization of a line in the same sense that you can talk about a tracing of the line, right? There is not a single way to do that. Okay. Alrighty. Okay, so reminder, parameterizations are generators, not testers. Case may come where you have a line in space and you want to test. I need an algebraic test to decide if, here's some points. I need to know which ones of these are on the line and which ones are not on the line. I have specific points I'm interested in. I'm not just looking to generate random points. How do you make a test out of a parameterization? There's a nice little trick here. Here's your parameterization. This parameterization, you'll notice, is in kind of vector form. I make the appeal that, of course, you can multiply this out with components. You can multiply this out in components. You can then add this to that in components. Two vectors are equal if and only if their coordinates are equal. So this, what you might call vector form of the parameterization, is equivalent to this, what you might call coordinate point of view on the parameterization. These two things say the exact same thing, just different ways. Okay. All right. Now, how would I use this to test? Well, here's a point that I'd like to know whether it's on the line. I just need to know, is there some value of t at which this parameterization generates exactly that point? Let me say that a little bit differently. Is there a value of t that generates the correct x-coordinate and the correct y-coordinate at the same value of t? Now, I emphasize it's got to be the same value of t. I mean, let's look at the following ridiculous scenario. What if I found, as my parameterization goes, what if it gives me the correct y-coordinate at one value of t, and then it gives me the correct x-coordinate at a different value of t? Well, that's not a hit, right? I don't need these equations to be true at different times. It's got to be at the same time. That's no good. Okay, so because these have to be true at the same time, what that means is I need for this value of t that makes this equation work to be the exact same value of t as that value of t that makes that equation work. And now let's just solve for what that would mean. Well, the value of t that makes that first equation work, a little algebra, there's what that value of t has got to be. What's this value of t right here that makes that second equation work? Well, again, solve for it, a little bit of algebra, and it's got to be that value of t. So I need for there to be a value of t that's equal to both of these things. And that's when I can actually turn this into a test. If I need for there to be a t that's equal to both of these things, then I need both of these things to equal to each other. If these two things are equal to each other, then that is the value of t that makes both of these, that's what you put here to make both of these equations work, and therefore that will generate that point. And this is a test. This is an equation. You give me an x comma y, and I can plug in and see if this equation does or does not work. Okay, so that's the little trick. Now, please do me the favor. Do not sort of memorize sort of the symbolic manipulation that, so whatever is here, that goes there. And whatever is here, that goes there. And whatever is, this one and that one, those go there, and there's your equation, right? That's not a mathematical argument. That's symbolic manipulation. It's also garbage. What if V1 is 0? That doesn't make any sense, right? So I do want to see, on any sort of a test, be it the midterm, even homework, right? If the question says, here's a parameterization, what's the corresponding equation? I want to see an argument along the lines of what we've written here. And it's sufficient to just say, look, t equals these two things, and therefore this. I mean, I don't need an essay, right? But I do need to see how you got there. Everybody on board? All right. Okay, so similarly, in 3 dimensions. Here's a parameterization of a line in 3 dimensions. There it is in coordinates. Multiply it out. We need to have a value of t that gets the right x coordinate, gets the right y coordinate, and gets the right z coordinate, and we need all of these to be the same value of t. Therefore, we need these to all be the same, and therefore, here's the test. Right? If you would like to have, if you'd like to know whether a given point is on a given parameterization, this parameterization, oh, whoops, I'm sorry. That parameterization is tested by this. Now, careful, that's not an equation. It's kind of three equations, right? I need these two things to be equal. I need these two things to be equal. And I also technically need these two things to be equal. Of course, if the first is equal to the second is equal to the third, then clearly the first is equal to the third. So you can call it two equations if you'd like. It's fine. I like to think of it as three equations. The terminology for these equations, by the way, this, I'm going to say trio of equations, is called the symmetric equations of the line. Symmetric because the three things that have to be equal are all kind of the same structure. Right? So, I don't know, I feel like that's plausible terminology. So, again, not exactly an equation because it's several equations, but nevertheless, this serves as a test. You give me an x, y, z, you give me a point and you want to know if it is or is not on this line in space, that's the test. Yeah? Okay. All right. Okay, cool little exploration of what these equations geometrically, how do I think about these equations here. I like this personally a lot. What does for example, one at a time, what do these individual equations mean? And neat observation, this one here, for example, the first you might say of the three symmetric equations. What is that thing? Well, first of all, it's a plane, right? I could take this and kind of multiply it out, and I would get, something times x plus something times y plus, well, there aren't any z's in there, but nevertheless, that something, 0, is a something times z that equals to something. This is literally the equation of a plane. And my normal vector happens to have a known third coordinate of 0, but it's still a normal vector. Right? Okay. So it's a plane. Second observation, any point that's on the line, well, okay, hang on. Any point that's on the line satisfies both of the symmetric equations. If it's on the line, then it also satisfies that one equation, right? That was a silly thing to say, but anything that satisfies the two equations also satisfies one of them, right? And so, therefore, is on the plane. Any point that's on the line is also on the plane. And another way to say that is that the line is inside of the plane. Or another way to say that, the plane contains the line. Right? So this thing that we're trying to understand, this thing here, is a plane that contains the given line. And then last observation, look at that normal vector again. This normal vector has no third component. This normal vector is horizontal. And if the normal vector is horizontal, right, that means the plane is vertical. Everybody see what I'm talking about there? Sorry for that. I can't do the visual aid for the viewers on the recording.
It just doesn't have the z axis.
Yeah, well, so the normal vector is in yellow there, and its third coordinate is 0. Mm-hmm. And if the third coordinate of the normal vector is 0, that means that normal vector is horizontal. Okay. Right? Because if that vector had any elevation to it, mm-hmm. it would have a z component, and this doesn't. It's 0. Yeah.
But it's still on 3 planes.
It's what?
Is it still on 3 planes?
Well, we're just talking about this one normal vector, okay. this in thing, right? Uh-huh. The normal vector that is associated to this one plane. Okay. It's just for that one plane. Okay. Yeah. So since its normal vector is horizontal, the plane is vertical. Okay. All right. Well, that allows you to draw a picture. And here's a pretty reasonable picture of it. Your line, purple. Your line, the first of the symmetric equations by itself is the unique vertical plane containing that line, and it's what I like to call the vertical shadow. Right? Just imagine, noon, sun, would cast a shadow down from that line and would make a plane that, the plane generated by the shadow, so I call it the vertical shadow plane. Right? So that's kind of a neat interpretation. In other words, the symmetric equations actually have geometric significance. Now I'm going to leave as an exercise for y'all. Take the argument that I just made, apply it to the other two symmetric equations, and I appeal to your intuition. Let me not say that. Go through the argument. There's several observations to be made. It's all analogous, but these other planes, the other equations in the symmetric equations are just other shadows. So, for example, you could talk about the shadow plane in the x direction, right? As if you were shining a flashlight from way far away down the x-axis, etc. Anyway, nice little exercise, something to think about. Okay. And I ran out of time. Sorry. So we'll call it here. Don't forget to turn in your homework. Remember, just a reminder, homework's always due at the start of class. If you came in late, make sure to turn in your homework. But please also, if you came in late, let me remind you, it's your job to make sure that I've marked you as present. And I usually, once the lecture starts, I'm not paying attention to who's coming and going. So make sure to come talk to me after we hit the stop button. Make sure I've marked you as present on the attendance sheet. Okay, see y'all later. And let me just hit this button here.